So 3.3 is basically talking about like how the derivatives affect the shape of the graph. Like from the previous sessions, we can talk about we talk about like local max and local min, the definitions of it, but never talk about like how to find those. And then we get a technique of finding absolute max and absolute min in a closed interval. But actually, when we are graphing it, we are what more important about is like the local max, local minimum, and how the graph is being like curved it upward or curved it downward, what we call it like concavity of those, and where the points of inflections are, meaning like where those like curve change it, from downward to upward and upward to downward, those kind of situations. So this section will allow us, specifically like how to get those value and evaluate it so that we can graph it better using the approach of a calculus. Right? So first up is like, we're gonna be looking at the increasing and decreasing tests, right? So before, you know, um, we know the functions increasing means what, we know the function decreasing mean what, and we can easily find out the interval of those when we are basically having a graph, but don't know, from just an equations or the functions, how do we do it? So this increasing or decreasing test will allow us, okay, to use and then find out the interval very easily. So first one is said that if the first derivative of the function is greater than 0 on a certain interval, and then we call that interval as an increasing interval. So I can use this inequality, right? I can basically use this inequality to basically find out what interval is going to be. So that's basically like uh, algebraic approach that we can do. And similarly, if f prime of x is less than 0 on a certain interval, then we call it is a decreasing interval. Okay. So why is that happening? If you look at it right here, okay, this portion of the graph from here to negative infinity, you can see that the slope of the tangent line is a negative value. Are we all following so far? Right? The slope of the tangent line is a negative value. So basically that's fall into these situations, right? That fall into these situations right here, right? The value of f prime is less than 0. So I can sort of see that, from negative infinity to up to 0, the slope of the tangent line is a negative value. So therefore, the function also is what looks decreasing functions right here in that interval. Continuing this, if I continue looking at it from 0, right? If I continue looking at this from 0 and all the way up to like, this point right here, and the slope of the tangent line is still what? Negative. Do you see that? The slope of the tangent line is still negative. So let me draw with like, another color pen. So you can see that the slope of the tangent line is like this. So it's negative slope. And right here is also a negative slope, right? And right here is a negative slope, right? Slope of tangent line. So you see that now from negative infinity all the way up to this particular point, the slope of the tangent lines are what? Negative, meaning what? My first derivative function value is less than 0. So also in the original function, what that basically happened is what? The function value is decreasing throughout all these points. Any questions before I move on from here? And if you look at on this portion right here, starting from, here, uh, you see that the slope of the tangent line is what? Positive, positive, up until, notice that right here that this point, the slope of the tangent line is a horizontal, which is 0, okay? And up until this point right here, the slope of the tangent line will become 0. But from this interval all the way up to here, and that is what? The slope of the tangent lines is positive. So that basically, you know, tell us, right, this situation is happening, right? So from here all the way up to this interval, the slope of the tangent lines is positive, so the function is increasing. And lastly, you can see that at the end, you know, from this point on to positive infinity, the slope of the tangent line is a negative again, which is what? Decreasing. You can see that the original function is decreasing functions. So the first derivative test, right? And what will the first derivative test allow us to do is to be able to find out where the local maximum and where the local minimum, those values going to be, okay? Where the local max and then local min is going to be. So the first derivative test say that, suppose that C is a critical number. So right here, let's say C, because according to the picture, I have 2p, right? So I'm going to explain it to you what are those. So C, these are my critical values, right? Critical numbers. Uh, of course, F has to be continuous functions. Then this is if-then statement. So you need to read it carefully, okay? So then it said that if what? F prime, means the function first derivative function value change from positive to negative at this critical number, then the function, okay, the original function has a local maximum at C. So that's basically talking about this situations right here. See from here, if you can see that at this critical number, my slope of the tangent lines is positive on the left-hand side. And then once it passed this critical number, the slope of the tangent line is what? Negative. So that imply on the first case right here, right? So the function, the function value of the function value, the derivative function value is changing from what? Positive to negative at that particular C, right? Critical number. Then we call that critical number as a local maximum on the original function. Follow? And similarly, the other way around, if we look at on this case right here, at this critical number, you can see that the slope of the tangent line is what? From negative to become what? Positive. Then that will become what? A local minimum at that critical number. So according to the mathematical statements, we are talking about what? The value of f prime changing from negative to positive at this particular C value in the domain, then we call that local minimum at C. Any questions before I move any further from here, right? So it's like positive, and then we have a local minimum at C. So that is very important, example right here. So for the last case right here, right? For the last case right here, when the derivative functions never change the signs, then we don't have a local maximum or local minimum, right? In the past sessions, I sort of shows you this graph before, x to the third power, y equal to x to the third power graph. So if this graph, if you look at it, it's like this, then you can see that the function, the tangent line is always positive, so it never changed, right? The tangent line never changed its sign. So this one's always increasing functions, always decreasing functions. Those type of functions does not have a local maximum or local minimum, okay? Or like in a certain interval of the functions, and in that interval is always increasing or always decreasing, right? Then we don't have any local maximum and local minimum at this point. So the next step is basically continuing and then looking at the other case, right? What is the concavity that I mentioned earlier, right? So you can see that On the left side of this point, the graph is upwards, and on the right side of this, on the right side of this point, the graph is basically downwards. So this portion is called concave up, and this portion is called concave down. And when we are trying to use calculus approach to graph functions, these are necessary also, okay? Because that way you can clearly see that, the graph will not be always like this, or the graph should be like this, so on and so forth, or the graph should be like this, okay? So the definition is basically like straightforward from what I mentioned. It's if a function f lies above all the tangent lines on the interval, then we call it a concave upwards. So you can see that right here, right? On this portion, on this interval, my tangent line, right? The graph is always above the tangent line, on top of tangent line. Then that interval is called concave up. And look at right here, the graph is always below the tangent line, and that is called the concave down, right? And this point right here, okay, where the concave up changes to concave down, that point is called point of inflections. Okay, point of inflections. So first, in order to find out point of inflection, first I need to know, how to find out the concave f, the interval of concave f and the interval of concave down first. So that has something to do with the second derivatives, right? So here's the concavity test. The second derivative basically state that if the concavity, the concavity test basically state that if the value of the second derivative is greater than 0 on a certain interval x, then we call this function is a concave upward on that interval. Okay, and if the function, the second derivative function value is less than 0, meaning it's negative, on a certain interval x, then we call that concave downwards. Okay, so with this, we will be able to, with this inequality, we will be able to find out where my concavity is going to be. Right? So now, with this definitions, I will be able to talk about how to find out point of inflections. So point of inflections, the only choice that I have left is point of inflections will be like using the second derivatives equal to 0. So let's go down a little bit more right here. So you got to be careful with these definitions. Okay, this definition can mislead you if you just look at right here. Okay, if you just look at right here and then think about, hey, if the second derivatives at a particular point is equal to 0, then that point in a function is called point of inflection. If you just look at this part, then that could mislead you. Okay, because there are cases that second derivative will give you what at a certain point the second derivative will be equal to 0, but it's not point of inflection. So let's start from the beginning of the definitions. A point of inflection p on a curve of y, y equal to f of x, a point p is called point of inflections if f is continuous, where the continuous there and then curve changes from concave up to concave down. This is a key part right here. Okay. Or another one is what? From concave down to concave up at the point P. Okay. So what is the point of inflections? When the concavity changes at that point. So like for example, this one that I mentioned earlier, at this point right here, the graph is concave up and changing into concave down. At that particular point, right, at that particular point C, and we will also get f double prime of C will be also equal to 0. So there are cases that you will not, you will get f double prime of equal to C, but however, it will not have a point of inflection because concavity doesn't change. Okay? So the key part right here is this part right here. concave up to concave down, okay? We need to check that. And as well as we need to check at that particular point, P, would that be like, f of A is, f double prime of A is equal to 0 or not? So before I continue, is there any question? So what the second derivative test basically talk about is this. At a critical number, so that means what, f prime of C is equal to 0, okay? And we have a critical number, and that critical number is inside the concave up. So this means, you notice that I'm interpreting the mathematical notation into the language, because f double prime is of C is greater than 0. That means at that point, that is what the shape of the graph is concave upward, right? So let me repeat it again. F prime of C equal to 0. That's basically talking about here's my critical number. And f double prime of C is greater than 0, meaning at that critical number, the graph is concave upward. And we can see that this portion right here, okay? We can see that this portion right here. See that I have a critical number at C, and also that C is in the interval of what, concave up. And what's happened? That point, that critical number become the lowest point in that interval. So therefore, with these two together, we can conclude that the function is a local minimum at C, right? So this is the second derivative test. And finally, the other one will be the same thing. Here, f prime of C equal to 0. Okay, I have a critical number at C, and f double prime of C is less than 0. That basically tells me that what, that critical number is in the interval of concave down. So we are looking at this situation now. Okay, we are looking at this situation now. Right here, we are looking at this situation now. Okay. Here's my critical number, and this critical number is in the interval of concave down, or at that point is concave down. Then therefore, this critical number becomes the peak, right there, which is the highest point. So that's how the second derivative test allow us to define where my local maximum is. So my local maximum will be at C. So is there any other questions before? So example 1, I'm giving to you a polynomial function with third degree, and we want to find out where the increasing and decreasing intervals are, and where the local maximum and local minimum of the function value, right? Function. And then also asking you to talk about the interval of concavity, right? Where is a concave up, where is concave down, and then also finding out the point of inflections. And after that, we can sketch it. So, to answer all of those questions, like for example, to talk about increasing, decreasing, local max, local min, and concavity, we need to know our first derivative and the second derivatives. So a lot of times in this kind of problems, I want to do my, I want to like take my first derivative and second derivative in the beginning of the problem so that I can use it later on, right? So taking the first derivative of these functions, right? And that will look like f prime of x, that is equal to 12x squared plus 6x minus 6. And when I take the second derivative of this function, that will become 24x plus 6. Now we got all of those already. So to answer part A, I need to, talk about the first derivative is like greater than, or the first derivative has a positive value, or first derivative has a negative value, right? Because what is the increasing and decreasing talking about? Here's a quick way of looking at it. And this is my number, like, where the f prime of C, this part C, is equal to 0. My first derivative is equal to 0. Because only if I find out my first derivative is where my first derivative is 0, then I can talk about the left side will be what? A negative value. My f prime of C will be less than 0. And on the right side will be what? My f prime, right, of C. I shouldn't say c, x, because any value on this left side of c will be negative, and then that will be greater than 0. So therefore, I can talk about the function is increasing or decreasing from there on, right? Because this will be what? Increasing function. This will be what? Decreasing. Oh, my bad. Sorry, the other way around. This will be decreasing functions, and then this part will be what? Increasing function for the interval part. So the key part is to talk about part A. What I need to do is I need to find out when the f prime of x is going to be 0. We need to find this first. Okay, so that I can continue from here. So this is what I want to know. What is my x value? So that's by saying that f prime of x equal to 0. So I'm setting up 12x squared plus 6x plus 6 equal to 0. Divide everything by 6. That will be 2x squared plus x plus 1 equal to 0. Are we all okay with this? Oh, I copied it down wrong. It's negative right here. See that? It's negative. Otherwise, it will mess it up, like, in the first problem. Now make it easier, because otherwise I will end up in, like, using quadratic formula, and I don't know what kind of number is going to come up, right? So right now it's like factorable, which is going to be 2x minus 1 and then x plus 1 equal to 0. So this gives me 2x minus 1 equal to 0 and then x plus 1 equal to 0. So I got x is equal to half and x is equal to negative 1. So we found out which x value, right, will make the first derivative functions going to be equal to 0. And that allow us, right, to write it on the real number line and then do the testing. And keep in mind that what are we testing? Okay, so here's negative 1, here's 1/2. And what we are interested in is finding out the value of, okay, we are interested in finding out the value of f prime. Finding out the value of the first derivatives. That's what we are interested in. So like before, what we're going to do is we're going to substitute, a few values into it and then test. So if I substitute 0 into the first derivative functions, so meaning if I substitute 0 into here, it will be 0, 0, and negative 6. So therefore, I got this interval will be what? A negative. And if I substitute 1 into f prime functions, then into these functions, then I will be getting what? 12, 6, minus 6 will be 0, so it will be a positive value. And if I substitute negative 2, now you don't need to really go into this part and compute over and over again. We already have a factor format already. You can basically check that also. When I plug in negative 2 right here, it will be negative value, and this will be negative value. So when I multiply it, it will become what? Positive value. So if you check it right here, it will give you the same answer anyway. So that basically tells me, where my functions is going to be increasing and where my function is going to be decreasing, right? Because according to the definitions of increasing and decreasing, right, tests, as long as, like, when we have, like, the first derivative function values are less than 0, then we call it the decreasing function, and then this is increasing. So here's another way to look at it also, right? Instead of writing plus or minus, and this way of looking at it also help you to think about the next question very easily and quickly also. So you can see that if it is first derivative value is increasing, positive, that means what? My slope is positive slope. And when the first derivative is negative, then my slope is negative slope. So it's going down like this. And then it goes back up right here. Okay? So you can think about this, writing out this arrow sign also. So plus or minus. Are we all following so far? Because by showing this arrow, then it will help you to see the shape of the graph also. You can see that what's happening. And on those critical point, we're going to have what either the highest point or the lowest point by looking at the first derivative test very soon. So now, my conclusion for part A, f is increasing on the interval of from -infinity to -1, not inclusive, union with from half to +infinity. And then we can talk about f is decreasing on -1 to half. That's the decreasing. So is there any questions before I move from to? So part B is asking us to find out where is my local maximum and local minimum. Right? So from the first derivative test, and it tells me that if the function value, if the first derivative value is going from positive to negative, then we're gonna have what a local maximum, and then the first derivative's value, right? The value of first derivative is going from negative to positive, then we have what local minimum. So now I can say that by first derivative test, and we have local maximum, where that will be f of -1. And we have local minimum at half. And the question is asking you what is the local maximum and local minimum value of the functions. It's not asking you where. So therefore, I need to evaluate to get the function value, meaning I need to plug it in this -1 into the original functions, because local maximum and local minimums are happening on the peak, right? The highest peak and the lowest peak of the original function. So you need to find out the function value on the original function. So I'm plugging back into f -1 into original functions, and that gives me 6. And when I plug it in, half, that gives me -3/4. Right? So those are the 2 points that will help us to do the graphing later on. So is there any questions before I move in? So part C is asking for the interval of concavity. So we're gonna approach it the same way as in increasing and decreasing idea, because concavity basically interval concavity, where the concave down basically say this, here at this C value, my f double prime of C will be equal to 0. And so therefore, f double prime of any value that is be left side of C, that will be less than 0. And any value of x on f double prime on the right side of C is greater than 0. So that basically means that it will be concave down on this side and concave up on this side. That's according to the definition that we have earlier, right? So what we want to do is like before, first up, I want to find out this. So to do part C, I want to find out where f double prime is going to be equal to 0. Okay, where f double prime is going to be equal to 0. We want to find that value first. And then we're going to use like real number line to try to test out the value of f double prime like before. Right? So here's the part, f double prime of x equal to 0. And I want to find that functions 0. So it'll be 24x plus 6 equal to 0. When you work on solving this equation, that will be -1/4. So this basically help us to see, right, where my f double prime is going to be 0. So I can basically use my real number line and then say that here is 1/4 power. And this time what we are interested in is we are interested in the value of what? The second derivatives, right? So as usual, I'm gonna substitute -1 on the left-hand side of the -1/4 and then 0 on the right-hand side. Since we want to find out the value of f double prime, we are substituting into here. Okay. So when I plug in 0, this will be a positive. When I substitute -1 and into this equation, then we got a negative. So what that basically means is on the left side of right -infinity to -1/4, we will get concave down. And from -1/4 to positive infinity, we're going to get concave up. Because later on, when we graph it, we need to make sure all of these, criteria is met, right, on our graph. So now that we got the interval of concave and concave down, so let's answer that questions. Right? Let's answer that questions. So concave up on the interval of from -1/4, right, to positive infinity. And concave down from -infinity to -1/4. Follow so far? And now, because of the concavity, right, it becomes concave down to concave up. Concavity change at this point, -1/4. And we can also answer the third part of this part C questions, which is a point of inflection. So we do have a point of inflections. That happens on what? F of -1/4. So what is this value? If you punch it in this -1/4 into the functions, that will give me 21/8 if you compute that. So now we answer all the questions part A, B, and C already. And using all of those, what we want to do is do part C. So in here, what I'm going to do is I'm going to place where my local max, local minimum, and then where the point of inflection is, right? So my local maximum is -1 and 6. So I'm going to make an increment of like 1, 2, 3, 4, 5, and then 6 right here, okay? And so therefore it'll be 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4. So we know that our local maximum, right? Our local maximum is at -1, 6. So here's our local maximum, -1, 6. And our local minimum is half and then -3/4. So half right here, -3/4 right here. That's our local minimum. And we have our point of inflection is -1/4. And then my y value is 21/8. So 21/8 is basically less than 3. Right? So 1/4 less than 3, 1, 2. So 21/8. Around right here. All right? So that's the best I can estimate. So now, by knowing the shape of the third degree polynomial with the positive coefficients, right? When the third degree polynomial with the positive coefficients, I know that my endpoint will be like this. And if you want a better graph, not just a sketch, because we only want a sketch. If you want a better graph, you're gonna be trying to find out where my zeros are also, right? Where they're gonna cross the x-axis and the y-axis, x-intercept and y-intercept. That will help you to get a better shape also. But here's the point, right? Our point is like to try to get the graph from what we just know. So if you look at, we know that it will be like concave down from this negative a quarter all the way to negative infinity. That will be concave down. So I know that my graph will be like this on this side, concave down to negative infinity. And would that, satisfy the 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 first derivative that we take or not, right? So which means that increasing and decreasing. So the increasing, the function is increasing from negative infinity to -1. So you can see that the graph is increasing all the way up to this point right here. That's good. And then decreasing after that from -1 to half, which is going to be here. So let me finish drawing on the other part, which is the other part. Concavity say that from -1/4 to positive infinity is concave up. So my only choice is like going down and then have a peak right here and come back up. And I don't know how this graph is going to come back up, like straight up like this, or maybe like, it will go like, wider on this side. So we don't know on those part, okay? If you want to know, you need to plug in more point to get a better precise graph. So right here, we're gonna come down and then have a peak and then go back up like this, okay? So it's concave up. So this point is point of inflections, and we have a local maximum and a local minimum right here. So by checking with the first derivatives, the first derivatives say that from -1 to uh, half, that will be decreasing. So the graph looks like it. And then from half to positive infinity, the graph is increasing again. So this check all the condition, all the criteria that we found out earlier, and then it matched. So the given function is cosine square x minus 2 sine x. And then we don't want to graph, endlessly. So it's given to you the interval between 0 to 2 pi. So in order to find out, increasing, decreasing intervals, critical numbers, local maximum, local minimum, concave up, concave down, I take the first derivative and the second derivative first. So when you're taking this first derivative, cosine square x, use the chain rule, right? So taking derivative of the power, so it'll be 2 cosine x, and derivative of inside, which is derivative of cosine, is negative sine x. Minus when you take derivative of the second term, derivative of sine x is giving you cosine x. So if you simplify a little bit, to make it easier for us to continue taking derivative on the next second derivative, I basically use the identity to rewrite the first term into negative sine 2x. So I don't have to use the product rule to like continue any further, right? So that make it a lot easier and shorter. And that's basically the simplifying part that I did. And I mentioned it before, and then we all asked before, like how far do we need to simplify it, right? And in trigonometry, it's as needed. So right now I use the identity, to simplify it so that I can make it easier on my second derivative. So now when I take the second derivative, again, I'm using the chain rule on the first term. So the derivative of sine is cosine 2x, and the derivative of inside, which is 2x, that will give me 2. Minus now taking derivative of the second term, which is derivative of cosine, that gives me negative sine. So when I simplify a little bit, that will become negative 2 cosine 2x plus 2 sine x. And as as in previous example, if you want to talk about increasing and decreasing interval, first I need to find out where my first derivative is equal to 0. so that, you know, I can use the real number line to test where my increasing, decreasing intervals are. So setting up the first derivative functions equal to 0. Now this time, you know, to make it easier for us to do the solving part, I'm not going to use the simplified one. I'm going to use the one that I just take the derivatives, which is going to be -2 sine 2x sine x cosine x minus 2 cosine x. We're going to use that part. So from here, I divide both sides by -2. And then after that, factor out cosine x, which will give me cosine x times sine x plus 1. And that allows me to find out, you know, each case, the 0 for each factor, which is cosine of 0 that happens on pi over 2 and then 3 pi over 2 within this interval that we are talking about right here, right? We are only interested in 0 to 2 pi. So therefore, those are the only two values that we have. So you really need to be strong on, like, you know, solving trigonometric equations and stuff, and also the identity of it. And the next one, I'm solving for sine x plus 1, move 1 to the other side, so sine x equal to 1. So which angle, right, of sine give me -1? The only thing, the only angle that I'm gonna get from between 0 and 2 pi is 3 pi over 2. So now that I have all the zeros already on the real number line, I can break it down into intervals to test out what is the value of the first derivative functions within those each interval. So is there any questions before we continue from this? So after we, you know, substitute the value, we got, you know, from between 0 to pi over 2 and 3 pi over 2 to 2 pi, that is the decreasing, right? The function is decreasing, and the function is increasing from pi over 2 to 3 pi over 2. So therefore, for part A answer, we got increasing will be pi over 2 to 3 pi over 2, and decreasing will be 0 to pi over 2, union with 3 pi over 2 to 2 pi. So from the first derivative test, you know, that will help me with the part A, and then from the first derivative test, it will help me to find out where my local maximum and local minimum. So like you can see that, bless you, pi over 2 is from decreasing to increasing, that it will be the local minimum. So I have my local minimum at pi over 2, and at pi over 3 pi over 2, I have from increasing to decreasing, so that will give me a local maximum, which is 3 pi function at 3 pi over 2. So when you do evaluate the value, this will be 2 and then -2 using your calculator, which is plug it into your original functions right here. Okay. So now we got part A and part B, and part C is basically talking about the concavity, right? So to talk about concavity, we are looking at the value of the second derivative functions, right? So first we need to know where at which x value the second derivative function will be equal to 0. So setting the second derivative function equal to 0, that means -2 cosine 2x plus 2 sine x equal to 0. And divide everything by -2, they'll give me cosine 2x minus sine x equal to 0. And I cannot factor or do anything, so therefore at this point I have to use identity to rewrite this equation so that we can solve it. Cosine 2x, I can rewrite it as 1 minus 2 sine squared x. So from here on, I will be able to factor it out, and which will get one factor is 2 sine x minus 1. And when I solve for this equations, we are basically solving sine x equal to 1/2. Right? So you can basically use, like, you know, the trig quadrantal picture to take a look at it, like, you know, what is the angles going to be. So 1, 2, radical 3, that is what the 30 degrees. So I got one answer is pi over 6. And sine is also positive in quadrant 2. So therefore, there's another 30 degree, which is 5 pi over 6. So we got two answers for the first case. And then moving on to the next one, sine x plus 1 equal to 0. So when I solve for it, sine x equal to -1. And this only happens on what? Between 0 to 2 pi, this only happens on 3 pi over 2. So now we got the zeros of the second derivative functions. Now put it into a real number line and then test it, each interval, what values of second derivatives functions you're going to be getting. So now take a minute to find. So after we testing the value of a second derivative on each interval, we got from 0 to pi over 6 and 5 pi over 6 to pi over 2 pi. Those are concave down, and between 5 pi over 6 and then 5 pi over 6 is concave up. So now I can write it down my concave up, the interval of concave up, that will become pi over 6 to 5 pi over 6. And my concave down, the interval of concave down will be 0 to pi over 6 union with 5 pi over 6 all the way to 2 pi. That's where we are interested in. So what is my point of inflection going to be? Point of inflection is where the concavity changes and also the second derivative is equal to 0. So the concavity change it on pi over 6, right? And then concavity change it on 5 pi over 6, those two cases only. And pi over 3, right? Notice that right here, 3 pi over 2, that's also what? That also, give the second derivative equal to 0, but however, there's no concavity changes, so that's why that is not a point of inflection, right? So that's why I pointed out earlier in the beginning, like when I was explaining to you, if you just look at second derivative equal to 0 is your point of inflections, you're going to get wrong because you need to check where the concavity changes also. So plug it in this value into the f functions, then we will get -1/4 and -1/4. Those are point of inflections that we're going to get. Okay? And confirm on those values. And is there any questions before I move any further? So first, what I'm going to do is I'm going to put all my local max and local minimum, right? My local maximum is at what? 3 pi over 2. And then that is basically, where is 3 pi over 2? That's going to go. Okay? Pi over 2 pi. Here's half. That's my pi. Let me put a notes right here. That's my pi. Okay? That's my pi. So 3 pi over 2, which is right here, half of it, okay? Which is, you can look at it this way. See, 3 pi over 2, and that will become what? Multiplied by 3, which is going to be 9 pi over what? 6. Right? You can look at it that way because I make an increment of 2, so to make it easier. 12. So right here, 3 pi over 2, which is going to be 2. That's my maximum point. Okay. And then the next one is like pi over 2, right? Pi over 2, which is going to be what? 3 pi over 6. So 1, 2, 3 pi over 6, that would be what? My local minimum, which is -2 right here. And then my point of inflection is pi over 6. Here's pi over 6, and then it will be a -1/4. So it will be, this is 1 unit, so a -1/4 right here. And then another will be 5 pi over 6. So 1, 2, 3, 4, 5, 5 pi over 6. Here's another point of inflection. Okay. And to make it easier and better, I'm going to plug in one more point, which is easily can be computed, right, for our functions. So when I plug in 0, my cosine square will be giving me 1. My sine will be 0. So therefore, what is 1, which is starting at this point right here. And when I plug it in 2 pi, it will be the same point that I will be getting. Okay, so I have those two extra points that help me to, start and end. Then from there on, we know that, from our uh, graph that we did before. So my concavity, right, concave upwards from pi over 6 to 5 pi over 6. So meaning like my concavity, concave up will be from here all the way to 5 pi over 6. Okay. So notice that there is a point of inflections that we have. And after that, we're going to have what? The concave down on the rest of it. So how do we draw concave down on this part? Let me use a different color right here. So this portion, like, from 0 to pi over 6 is concave down, which is going to be this part right here. And then from 5 pi over 6 to all the way to 2 pi is also concave down. So it'll be getting a peak and then come back down like this. Okay, so that's the best I can draw with on this pad, but that's only using concavity part, right? Now let's check, does it also, satisfy, the increasing and decreasing that we are talking about. So we know that from negative infinity, from 0 to pi over 2, which is all the way up to here, right? 1, 2, 3. That is what? Decreasing. Yes, we have decreasing. And from also from 3 pi over 2 to pi over 2, that is decreasing. Yes, that's right. That matches. And then pi over 2 to 3 pi over 2 is increasing. So it basically satisfies all the cases that we did before. So therefore, this is my sketch of this graph.